Thanks, Anita. Just start this sharing. Okay, can you see? Can someone confirm you can see this again?
Yeah.
Cool. Thanks. So yeah, as Anita suggested, I am going to be talking about sort of inverse modelling work of CO2 emissions from Europe, but I'm going to particularly kind of focus on the UK, given the sort of focus of DARE, and talk about how we might be able to use carbon monoxide then or whether we can use carbon monoxide as a co-tracer for fossil fuel emissions of CO2, or particularly combustion emissions of CO2. And just to sort of get this started, then I mean, on this slide, I've just put the distribution of emissions from the UK's national inventory, so the NAEI, which I might refer to quite a lot through this talk. So this is just plots that they have up on their website for CO2 and CO, and so you can just see the sort of similarity already in the distributions of those emissions, primarily concentrated around urban centres and the road networks, and because these are both produced from obviously combustion processes, this is why we expect similarities. So I'm just going to talk a bit about what kind of approaches for estimating CO2 emissions, why we might be able to use CO, and then sort of lead into some of the inversion approaches that we're exploring, and then some quick results as well. And just, I'm not going to go in too much of an intro because I think everyone's going to be very aware of kind of the situation, but these are the UK's estimates of CO2 emissions that they produced. This is from the 2020 inventory report, and just showing sort of levels of CO2 emissions and the decline, particularly since about 2008 that they estimate. And of course, what we want to be able to do is evaluate that through atmospheric data and say, well, is this real? Are these estimates accurate? And is this decreasing trend happening? Can we see that in the atmospheric data? And we also, and so at the moment, this is something that we don't really do, but in a similar way to something that Alistair would do for methane, is can we then produce, so this is a plot that appears in the sort of annex of the inventory report. This is for methane, where he's comparing estimates from the atmospheric data with the inventory totals, showing that they compare reasonably well, and you can actually see this sort of small decreasing trend in methane over the last 8 years, reflected in both the inventory and the atmospheric estimates. And of course, so one of the reasons why we don't really do this is because traditionally, like the traditional approach is just to assume that fossil fuel or anthropogenic emissions of CO2, we just assume that they're well known. And this isn't to pick on this paper. I mean, I'll just go ahead. One had easy access to it, and it's focused on the UK. But so this is from Emily White's paper from a couple of years ago, which was looking at CO2 emissions of the UK. And the approach here is fairly sort of typical, basically, of inverse modelling. It's just that we assume that the anthropogenic component essentially is fixed, and that's shown by this grey dashed line. If you can see my cursor anyway, it'll point out around the top. So this grey dashed line, that's the sort of fixed anthropogenic and also ocean component. And then when looking at the differences between observations and our models, we're then prescribing all that difference to be due to differences in the biosphere. And this, you can understand this approach because we have much more uncertainty in the biospheric terms, and we think we're much more certain about the fossil fuel emissions. So that's why we generally take this approach. But what that means is then we can't actually look at whether these fossil fuel emissions are right or not. So approaches to kind of look at that are generally sort of based around using radiocarbon measurements. So using the isotopic composition of, say, delta 14C. So hopefully everyone's aware that fossil fuel emissions are very depleted in delta 14. And so this is a plot comes from a paper from Suresh Basu from last year for the US, where they're estimating fossil fuel emissions of CO2 there, and the blue show the priors that are used, and the pink lines show their posterior estimates. And then these posterior estimates then agree quite well with an independently compared inventory. So this is all very well and good, but obviously there's a few issues. One is that this paper was published in 2020. It's reporting on 2010, so it's quite a long time lag there between maybe getting these measurements and getting the results. I'm not really sure the reason for that. But then also, obviously, these measurements are fairly infrequent, expensive, and so on, and hard to take. And then in addition, in the UK, particularly, we might need to look at the effect of the nuclear power industry on these on this radiocarbon signature. And so that was one of those well, sort of point that Angelina's paper made in particular about the influence of nuclear power. So it's shown in this figure here. So the light colors show we're getting a lot of influence of nuclear signal. And even if we do have those measurements, we don't have them that frequently. And so then generally the approach is to then try and increase the frequency by calibrating with carbon monoxide. So if you're measuring, say, carbon-14 every 2 weeks or something, and then calibrating the ratio then of the fossil fuel component of your CO2 with CO, and using the CO-data to effectively fill the gaps between when you don't have any carbon-14 measurements. But the question, so the problem here is that you need these carbon-14, and we might have some in Europe and in the US, but we're not going to have that around the world. And then particularly in the context of using satellite data, which is obviously much more global in its coverage, clearly never going to be able to detect carbon-14 from satellites, given the sort of lengths have to go to get it in situ. So can we can we use an approach which doesn't rely on carbon-14? And so really that's the question kind of asking, do we need this? Or can we just use carbon monoxide alone as a co-tracer of emissions? And potentially we could use some other co-tracer as well, like NOx, but I guess for the purpose of this talk, I'm just going to focus on CO. And so there's reason to suspect we can if we just look at the atmospheric data. So here I've just plotted carbon dioxide and carbon monoxide at Tackleston. And this is from the winter, going from December 2017 into February 2018. And they're on different scales. So carbon dioxide is plotted in purple, and that's the scale on the left, so it's in ppm. And carbon monoxide is in orange, scale on the right, and it's in ppb. But just by overlaying those axes, you can then actually see that these two things really overlap each other. So when you get peaks in one, you get peaks in the other. And so potentially you might not even need carbon-14 essentially, because it's just a very strong relationship here in winter when the biosphere activity of CO2 in particular is suppressed. And if you just scatter plot these two together, you can see there's a very clear linear relationship between those two. So the reason for that, I guess as we kind of said, is that they have similar emissions distributions. So for CO2, just going back to this plot, and then again, this is just for the UK, you can see that emissions are predominantly dominated by from the energy industries, transport, processes, and residential emissions. And then for carbon monoxide, slightly different, but it is fairly similar. So we've got a lot of large contributions from residential combustion, also the stationary combustion sector, which is somewhat different. I think in this case, it's probably referring to things like generators. Road transport is a much smaller component now. So if you look in 2018, the road transport only accounts for about 14% of emissions. Obviously, going back into the 1990s, it was a much larger component. But sort of improvements in transport regulations of emissions have sort of significantly reduced CO emissions from cars and so on. But there's enough overlap there between the sectors that they this is why we see this strong relationship in the atmospheric data between them. And so if we then plot these up, again, just a sort of slightly different version of those plots from the opening slide, then you can see similarity in those emissions distributions, but predominantly focused on urban centres. But if you look at the ratio, so this is now looking at the molar ratio between CO and CO2, and these are data from the UK's NAEI. You can see, so this is showing the CO over the CO2 molar ratio. So low values, blue values in this plot are indicating less CO2 per molecule or per mole of, sorry, less CO per mole of CO2, whereas reds are indicating more CO. So what you see is that basically we get smaller ratios in areas such as London, Midlands, again, essentially urban areas. Rural areas tend to have higher ratios, and this is due to differences in the different sectors. So for instance, if you look at something like road transport within the inventory, we have a sort of very similar ratio all around the country. Although partly that's just the scale of this plot, but you can always pick out sort of like the M25 around London. Whereas if you look at something like domestic combustion, so our boilers and so on, then this is where you see a real urban-rural divide. So basically, urban emissions here seem to be a lot cleaner in the sense of less CO compared to more rural areas. And so if you then, I mean, that's just looking at the UK. If you look at sort of all of Europe, then the picture gets even more sort of complicated. So these are some plots on the other postdocs in Edinburgh, Melia, Sadiq made. And these are for different sectors across Europe. And yes, sort of scale bars are slightly different. But in this case, blue, light colors like blue and white are indicating not much CO per CO2, whereas red colors are indicating more CO for each mole of CO2. And so you see the things like public power, where they can probably much more control about what they're emitting and capturing the CO, or making sure that combustion is more complete. Then you get these very low ratios, whereas for other sectors such as stationary combustion or off-road emissions, you see much more CO per CO2. But the other thing to note is obviously for different countries, you get very different ratios. So these, the mapping here is from the work done with TNO, and where they're taking the country totals from the UNFCCC submissions, and then mapping these for different countries. But then so you just get these big discrepancies at the borders because each country essentially assumes different ratios essentially of CO to CO2. So there's basically, I think, a lot of uncertainty. That kind of highlights how much uncertainty there is in these emission ratios, because it's highly unlikely that such sort of large discrepancies exist in real life. And so that then sort of complicates this picture a bit more. So when we look at something like this overlaid data, you can't just sort of take the CO data and use that to estimate the CO2 emissions. And in winter, although we see this nice relationship here, in summer, you kind of lose that completely anyway. And part of that obviously is due to the enhanced biospheric activity of CO2, both in terms of uptake through photosynthesis and also respiration, but also due to differences in the way CO is produced and destroyed in summer. So basically it's very hard to pick out any sort of relationship between the two, between this is June and August of 2018. And so one of the reasons for this, particularly with CO, is actually in summer there's quite a strong chemical source of carbon monoxide in the atmosphere, and this comes from the oxidation of methane and also non-methane VOCs. So what these plots here show are just some modeling of using sort of inventory values and model outputs of the chemistry to estimate the component of the enhancements that we see at different sites due to either anthropogenic or sort of this chemical source. So showing us the Billsdale site in the top left, Heathfield, down in Sussex in the top right, Tapperston in East Anglia in the bottom left, and then this site here is in Sweden in the bottom right, just to show that this effect can be really pronounced actually. I mean, it tends to be a bit more pronounced over Europe than it is in the UK. And so the green lines here show the effect of the chemical source on the enhancement, and then the orange line is the estimated anthropogenic component. The blue is the observed enhancement, but where we've had to just calculate this by subtracting some estimated background level, which might not be very accurate, hence why it goes below 0 at times. But what you can see is that there are times, particularly for certain sites, so maybe at Bilsdale and Tapperston, where the chemical source is much more important than the anthropogenic. And this is again, particularly at the site in Sweden, that actually this is even more noticeable. This green line generally above the orange for large periods. So we'd need to kind of take that into account. But just to note that in winter, this really isn't an effect, because we don't have the same chemical source, basically. And just say then that this summer chemical source potentially affects what you can see from satellites, or what you can see directly from satellites anyway. So this is again a plot taken that Mello made. So plotting the Chapomi columns of CO in the top left here, and this is from July. And basically you can't see any sort of correlation really with sort of anthropogenic signals that you can see in, say, NO2 data from Chapomi. And potentially, I mean, you can see a little bit perhaps here in the Ruhr region in sort of West Germany, maybe the Po Valley as well. But this chemical source essentially could be masking a lot of the anthropogenic information that's seen in NOx. And then I kind of include this satellite slide just to highlight the issues of perhaps using satellite data to constrain things over Europe, just because this is sort of the best that we have at the moment from OCO2, the OCO2 satellite for CO2. And summer is when we expect to get the best satellite coverage. Fewest clouds, we've got most daylight, the angle of the sun allows us to see further north. But even then, the data coverage for CO2 is relatively sparse when you compare it to, say, CO or NOx. So in terms of actually how we estimate these CO2 emissions, well, there's kind of been a number of, well, there's a few approaches that have been used, and one of them is to try and exploit the correlations in errors between CO2 and CO. So this was an approach kind of first used by Paul, I guess kind of a while ago now, maybe about 15 years ago, using data from East Asia. And the idea is to exploit correlations in activity data and emission factor errors to help between CO2 and CO to help constrain these fossil fuel emissions. And this was also then developed slightly further by others in the Harvard group a couple of years later. But one of the findings of Paul's work really was that actually these correlations need to be quite large in order for this approach to be effective. And that's shown in this plot in the bottom left, where the red squares are showing the posterior uncertainty, and the black ones are showing the magnitude of the posterior source. And so basically, it's only once you get to a correlation of about greater than 0.7 that your uncertainty becomes smaller than your actual, than 100%. Basically. So if you have a very strong relationship between these two things, then this could be a very effective approach, but otherwise perhaps it's not really helping to constrain things as much. So how can we calculate these correlations? So essentially we just kind of take a simple idea here that emissions are equal to some activity data multiplied by an emissions factor for each sector, and you can break those sectors down as much as you like. And so then the errors within the emission errors are then related to the errors in each of these terms. So you have some activity data plus some error in that activity data, and an emission factor multiplied by an emission factor plus some error in that emission factor. And then the idea is that activity data errors should be shared between carbon dioxide and carbon monoxide because they're being released by the same processes. So if your number of cars on the road increases by 10%, that should increase your CO2 emissions by 10% and also your CO emissions by 10%. And conversely, emission factors and their should be inversely correlated. So because CO is released from incomplete combustion, if you decrease the amount, if you decrease the amount of CO that you're emitting per unit of fuel, then you should be increasing your amount of CO2. And so if we use these and we run those through, so this is using error statistics that have come from the TNO group they've produced, and they've provided some really detailed analysis of the errors within the European inventory submissions. And we can try and run these through a Markov chain, a Monte Carlo approach, and estimate the correlations then between the errors for different countries. If we assume these, so we have this perfect correlation between activity data and a negative correlation between emission factors, then sort of magnitude of values that get out sort of range anywhere from sort of minus 0.1 for Belgium to about 0.5 for the UK. Even so, these are still quite small relationships then between the countries that kind of fall short of that 0.7 that was mentioned earlier. But then the other issue is that perhaps we're overestimating the relationship in emission factors. Because if we actually look a bit more in detail at different sectors and the relative errors of the emission factors, what you see is that, well, for CO2, the errors in the emission factor for each sector is generally around 1%. Whereas for CO, we might be talking about sort of 20 to 50%. But in terms of the actual magnitude of their emissions, they're obviously very different. And so what this means is the component of the CO2 emission factor error that you essentially could prescribe to CO is only of the order of a few percent. And that's shown just those calculations there in the right-hand column. Other than for off-road emissions in this sector breakdown. But this is because of the sort of relative magnitudes of CO to CO2 emissions and their emission factors. And so if this is the case, then actually maybe there isn't such a strong negative correlation between these emission factor errors. And then if we make that assumption, then essentially all relationship between these two basically disappears. So it's really unclear actually whether this sort of joint error information would really add any useful information to our inversions. And in addition to that, it's really difficult to see how we could, although we have these statistics, and these really nice statistics on a sort of national level, it's hard to see how we could then scale or downscale that to a sort of grid box level where we're looking at, well, what's the activity data error on a 25-kilometer grid box? And so that kind of makes this a bit more complicated. And so for that reason, just want to explore then other approaches that we could use. And so one thing is well, we can still kind of follow this idea that we have these errors in activity data and emission factors, but can we just sort of solve for these sort of more directly within our inversion? So, like I say, we have sort of shared activity between carbon dioxide and carbon monoxide. So we could have one term essentially that scales that activity data, and that would affect both our comparisons to CO2 data and also CO data. But then our sort of ratios between CO and CO2 emissions are also uncertain, so we need to take that into account. So then essentially we have some other, if we imagine, so we've got some grid, some domain, each grid box within that domain, we can split this into 3 layers. So one layer would describe this activity data, and then a second layer essentially would describe the emission factors, or the emission ratios. We could change that emission ratio of CO to CO2. In effect, that would only affect the CO data because of the sort of relative magnitudes of emissions. And then our final layer will be for the non-combustion, so essentially the biospheric source of CO2. So this is just something we've been exploring recently, and so using the nested geoscan model, about 1/4 degree resolution across Europe. And then using data from 22 different sites, so from both the ICOS network and then also UK, deck network as well, and using an ensemble Kalman filter inversion approach to try and estimate things at a grid box level, and using, so basically scaling priors of biospheric and ocean and anthropogenic activity and emissions. So one thing to look at as well, is this going to be any better than just randomly, well, not randomly, but just solving independently for a biospheric CO2 term and a fossil fuel CO2 term. So in order to look at that, we can set up a pseudo experiment where we want to see whether we're improving our estimate if we use this sort of ratio approach, whereas compared to if we just solve independently. So to do that, we're then looking at the difference between our posterior emissions X here and the truth relative to our starting point. So basically, the closer the value this is to 1, the better we're doing. And so what we can see is that we do seem to improve slightly. The gain here is fairly small compared to if we just solve these things independently. Partly is because this is just the gain across the whole domain, so we've just average things over the whole thing. But so it might be if we were looking at more specific, just say looking at the UK, you might see, hopefully, might see more stronger gain in going from the blue results here in these bars. These orange bars hopefully might be slightly higher. But there does appear to be some improvement, so maybe this is working, but we need to look into this more. And then if we look at this in terms of real data, so this is really preliminary results, so I really wouldn't get too excited about anything I show, because I only got this finished last week. But just looking at 2 months, so July and December, and this is just looking at the UK estimates of the UK CO2 flux. So orange shows what the prior estimates were in each month, and then the purple is showing if I'm using this sort of joint shared information of CO and CO2, whereas the turquoise is if I'm just solving for CO2 independently, but solving for both the biospheric component and a fossil fuel. So the totals actually come out quite similar to the results of Emily White's paper. I mean, admittedly from very different years, but I think that sort of the magnitudes seem to be in the right ballpark for summer versus winter. So that's at least something that looks reasonably sensible. But these totals seem to be a bit quite different than between these different inversion approaches, which doesn't quite seem right, because I feel like the total CO2 shouldn't really depend on the approach that you're using. It's more the partitioning between the biosphere and the anthropogenic terms that should. So there might still be some issues we need to look at here. And then if you look at the sort of different sectors then, so we've got the non-combustion, essentially the biosphere on the left, and the combustion sector on the right. So this biospheric term seems to be reasonably well, it doesn't make too much of a difference then using one inversion to the one approach to the other, and there's no real change in the uncertainties on that. But then for the combustion sector, we see that get quite a difference then between if I'm using the information from CO or not, and it does result in a really large decrease in the uncertainties. The only thing. I'm not sure if the relative magnitude of these uncertainties is believable, but I think, if the absolute value of these uncertainties is believable, but at least there is a decrease relatively from if you don't use the CO information to if you do. So this is still very much a work in progress, and we really need to determine whether this is actually an effective approach or not. And then the nice thing then is that you can potentially look at distribution, how that distribution changes across the European domain. So on the left, just looking at the difference between the posterior and the prior for the non-combustion sector in December, and essentially seeing large decreases over a lot of sort of the north and west of the UK, whereas for, say, the combustion sector, seeing sort of decreases around the Midlands and then increases in other parts, and then particularly in sort of the Benelux and the Ruhr regions. But yeah, like I said, I'm not sure how believable this is, and I think there's still some issues to iron out within this. So just to sort of summarize all this, I think there is the potential for CO to provide useful information on combustion emissions of CO2. Just sort of get, now around to setting up this inversion system that's solving for these, both the shared activity data and also altering the source ratios between CO2 and CO2, but sorry, between CO and CO2. But we still need to determine really if this actually is improving our, or rigorously determine whether it's improving our CO2 estimates. So not the most conclusive conclusion, sadly. And so I thought I'd just be trying to end a bit more provocatively, really, and try and prompt some discussion, which is, well, is there, how much point is there to this work? Because it seems to me that policy a lot now and attention is focusing on net zero. So, and it seems that establishing the net CO2 emissions on a national basis is much more achievable using atmospheric data than, say, trying to isolate this fossil fuel component or isolating different sectors. So that seems like something that we can achieve using atmospheric data, whereas it seems that something harder to achieve from an inventory point of view, because although they might have good energy statistics, it's quite hard then to work out the drawdown from managed land and so on. And so is this really actually where the atmospheric CO2 data, the focus of that should be used more as looking at the net CO2 budget of a country rather than seeing if we can isolate exactly what's coming from, say, the transport sector or something. But I'll leave that open-ended question out there and finish there. Thank you.
Okay, thank you, Mark. I think we have time to do some questions with Mark now before we move on to the next talk. So I think maybe the best way is just to raise your hand, use the raise hand button. Okay, is it working? Ah, there we go. Not really sure I can tell what order they come in, but I think, Matt, you're showing up first on my list. Matt Rigby, that is, sorry.
Is that me, Matt? Yes.
Yeah, I forgot there's two of you. Sorry, Matt Rigby was first on the...
Okay, sure, I'll be quiet.
Oh, sorry. All right, thanks. Thanks, Mark. That's really interesting. Well, I'll let other people comment on the what's the point thing. I guess just some technical questions. I mean, it looked like, first of all, how are you solving your inversion? Because it becomes a bit non-linear, doesn't it, if you're including these ratios in the inversion itself? And also in your results, you seem to have no seasonal difference between your anthropogenic CO2 flux.
Yeah.
Discuss.
Yeah, I mean, yeah. So I mean, this is why I don't necessarily believe those results in the minute. But in terms of the non-linearity, I think so. Not actually, I guess. So one term then is scaling both the CO2 and the CO emissions together. So increase both by 10%, and then the second term essentially then is only altering the CO emissions. So it's changing the ratio by then essentially adding a residual term that's changing the CO, but not CO2. So I don't think it's a non-linearity.
Okay, got it. All right, thanks.
Matt Williams, you've disappeared from my list. Is that on purpose, or did you still have a question?
Yeah, I mean, I'm interested in Mark's point of the bigger questions at the end. So it would be good to discuss those. But it sounds like what you're saying, Mark, is that what we should rely on the inventory data to tell us the fossil fuel emissions, and then use the satellite information to give us the net fluxes. I mean, it sounds like combining a bunch of different information sets with the atmospheric giving us a sort of overall budget constriction.
Yeah, potentially. Well, yeah, it's just more a question of what should be our focus. Like, should we be trying to do something here with atmospheric data that is probably quite hard to see, and where we think that we know these anthropogenic emissions to within plus or minus a few percent, which we're not going to be able to achieve through that same level of confidence, I don't think, through atmospheric data. But what we can probably achieve is a level of confidence on that net budget.
Sounds like you answered the question, Mark.
Well, no. I think it's a point. I don't know what other people's thoughts on that are, but yeah.
Well, Mark, just following up on that is, you mentioned managed lands as a big component of this. Obviously with the atmospheric data, we would need to sort of designate what are the managed lands and what is, what is that? I guess my question is, how would that, from the atmospheric, top-down perspective, do you think that it's just going to simply be a case of we pick out which grid cells are managed and that's what we call managed, or how does that fit into that kind of question of net zero with the top-down?
Well, I guess it depends what net zero means as well, doesn't it? Like, does each country say that all land, all uptake within their borders is part of their emissions, right? So, I mean, or is it only the managed land that they're counting and so on? Like, I mean, yeah. I don't know. Yeah.
If you can give us net zero at a small spatial resolution, then in every one of those pixels, if we have the bottom-up estimate of fossil fuel emissions, and then we produce our managed land estimate from our biogenic modeling, then we've got lots of different pixels to test whether we're getting everything to add up properly.
Yep.
Mm-hmm.
Can I just point out, obviously, that in the UK, all land is considered managed. That is not true of all countries. Canada, for instance, has a large unmanaged area, but the UK does classify all its land surface as managed. So therefore, its emissions, by my understanding, therefore, is that all emissions are counted from across the land of the UK and are part of the LULUCF. So, for instance, peat, etc., which makes it easier in answering the question for the UK. Makes it harder for Canada, but easier for the UK.
But does the LULUCF include forest growth, for instance, or is it just about land use change? Is it just about changes in forest area, or does it actually deal with the state of carbon accumulation in forests?
It should count for both, because it's land use, land use change and forestry. So my understanding, again, I need to clarify all these points, but I think, in my view, that should count everything.
Yes, it does. Oh, forest growth count.
I mean, I think there's a really complicated topic, the LULUCF side of this, and I wonder if we actually need to spend some time thinking about that in more detail. It gets quite technical, what is counted and what's not, and various things. So I don't actually know that much about it, but maybe Matt's something that we should think about for another sort of offline meeting. All right, who's next? Heather.
Thank you. Thanks, Mark. I was going to ask about the chemical production of CO. So is that's the net production minus the sink, is it?
Yes. Yeah, obviously sink's quite important for CO as well, particularly in summer. But
and then how do you treat that in the inversion? Is that part of your uncertainty, or?
So yeah, at the moment I've just got that in as a sort of single term describing the magnitude of that net chemical, or each net chemical source, so the CH4 source and also the VOC, the non-methane VOC source, because they've got different distributions. So yeah, there's just one term that's scaling each of those for the entire domain, basically. So this is using output from a full chemistry run of GeosChem model to produce those distributions of chemical production.
But you're considering that there's some uncertainty in that as well?
Yeah.
Yeah, okay. And then would it be helpful to know what the fossil fraction of the CO is, do you think? just to confirm that you're
fossil fraction of the CO, as in terms of isotope measurements.
Yeah, because I mean you're linking basically fossil CO, but you can only measure total CO. It's kind of the same problem as we have for CO2, but just to check that you.
Yeah, I mean, I think
properly.
definitely, like, I don't know because how verified this sort of chemical source output has. I mean, it has to some extent, you know, in comparison in terms of total CO to measurements. But yeah, if it was in terms of if you could actually separate between what was the fossil source and what wasn't, then that would definitely help establish how accurate this sort of model output of chemical source was.
Yeah, it might be interesting to look at a different chemical model as well to see how different
Yeah.
it was.
We have, sorry, a couple more questions, but I'm just looking at the time. So, Alistair, Angelina, would it be okay if we kind of push yours to the end and make sure we have enough time for our second?
Yes, of course.
Okay, great. So I think with that, we will move to Ingrid now. And then after Ingrid's talk and her questions, maybe we can come back and actually do a few kind of questions as a group with everyone. So any leftover questions we'll do then.
Can you see my screen now?
Yeah, I can.
Okay, good. Oh, thank you for the invitation. First of all, I'm very happy to be here. For those who don't know me, my name is Ingrid Super, and I have a background in inverse modeling. But a couple of years ago, I started working at TNO, and now I mostly work on emissions. And I shortly want to introduce the team that I work in, because I think it's very interesting and very unique that we have actually two expertise under one roof in one team. So we have a group of people working on emissions, mostly the compilation of European emission maps for both greenhouse gases and air pollutants. We also recently started working on emission modeling and uncertainty calculations. If you're interested in more details, I would like to refer you to the presentation given by my colleague in the same seminar series a couple of months ago. I think you can see it online. And then we have a group of people working on the modeling side, also inverse modeling across different spatial scales, using different types of models and statistical techniques. But what for me personally is the most interesting part is where the two come together. As I said, it's quite unique to have both these expertise under one roof. And what we try to do is to see what is the impact of choices on the prior on the inversions, and what can we learn from the inversions on how to improve our emission inventories. And yeah, this will be the main topic of my presentation today. I start with an equation. It's not something that I normally do. I hate equations in presentations, but I made an exception here because I think it's useful to see what the role of the prior is in an inversion. So basically this equation is the cost function that you try to optimize in an inversion. So you're looking for the minimum of this function. And there are two terms. The first term is related to the comparison of your model and your observations. And then the second term is related to the prior. And in both terms, you have an uncertainty, which basically is a weighing factor because it determines how much weight is given to either the observations or the prior. So how much information do you take from both of them? So let's say you have very good observations and you trust them completely and you really do not know very well the prior emissions. These terms basically ensure that in the end you end up with emissions that if you put them in your forward simulations, they're very close to the observations. But also the other way around, if you have observations that you do not really trust, but you do have a very good prior, the optimized emissions will be very close to the prior. So these two factors, these uncertainties, are very important in determining basically where you end up with your inversion. So it's very important to really think about these terms. And also the choice of the prior is very important. You can optimize emissions for a whole domain, or you can optimize gridded emissions. Basically anything is possible, but you do have to realize that when you go to higher spatial or temporal resolutions, it usually also means that you increase your uncertainty. So you need a stronger constraint from your observations eventually. Another option besides optimizing the emissions themselves is to optimize an emission model or the parameters of an emission model. And I want to say something more about that. So these emission maps are basically what we normally use, what modelers normally use. It's very simple. And it's, well, for example, the European inventories that TNO makes are based on country reports. And most countries also report their uncertainties in the activity data and emissions factors that they use. So it's relatively easy, still not very easy, but relatively easy to estimate the uncertainties in these emission maps. And I will show you a bit later in this presentation how we do that. The downside of these emission maps is that the uncertainties are relatively large, especially for if you cover a larger domain. So for example, the temporal downscaling is often based on long-term average activity data. And it's not country specific, or so this introduces an additional uncertainty. And what is also a downside of an emission map is that you basically only have the emissions and not the underlying data that are used to calculate these emissions. So actually what we do is we gather all this data, activity data, emission factors, and spatial and temporal scaling factors. But what we deliver is just the emissions. So if you optimize emissions and you find that the emissions should be larger than the prior, you do not know exactly where this change is coming from. So that's one of the reasons that we recently started developing an emission model to overcome some of these limitations. So an emission model basically uses local activity data that represent more of the spatial and temporal variability in the emissions. And all the data are explicitly visible in your model. So you can optimize these as parameters instead of optimizing emissions. This also reduces the size of the problem because emissions change from one grid cell to the next, but an emission factor of CO2 is relatively stable within a certain domain. So you only need to optimize this emission factor. However, it's also more difficult to estimate the uncertainties in an emission model, whereas fuel consumption can be directly translated to CO2 emissions. Using, for example, traffic counts is, translating that to CO2 emissions is more difficult. So you add some uncertainties there. But if you can do that, it does give you a lot more insight in what causes changes in your emissions. Is it related to an increase or decrease in fuel consumption or activity data, or maybe our homes are insulated better or whatever? And this kind of information is very interesting for policymakers, also to assess the efficiency of emission reduction policies. So I give you an example of what it looks like to optimize an emission model. You see here the domain that is used, and this is the west coast of the Netherlands. Here you have the city of Rotterdam, The Hague, and Amsterdam. This is a synthetic experiment, so without any real observation. So I can already tell you that this actual scaling factor should be 1. And the dots give the prior scaling factors for the emission factors of a couple of source sectors. We assume here that the activity data are well known and do not have an uncertainty. So we only optimize emission factors. And then these box plots give the spread in daily scaling factors for a period of 14 days. So 14 scaling factors in total. And we only use CO2 observations here. And what you see from the results is that the largest spread is seen for the emission factor of sector 3, which is the industry. And the reason for this is that the industry is very dominant in this area. But it's also the most uncertain in this case. So the cost of optimizing this emission factor is very low. What we can also do, we did the same experiment again, but now with CO-emitted species. And the interesting thing of CO-emitted species, well, Mark already showed you a bit on how you can use CO to distinguish between fossil CO2 and biogenic CO2. But it's also, these CO-emitted species can also be used to distinguish between source sectors. Here on the left side, you see the emission ratios of CO to CO2, NOx to CO2, and SO2 to CO2 for a couple of sectors. And you see that some of these sectors actually have a very distinct signature. So what we try to do now is we include the observations of these CO-emitted species in our inversion to basically say, okay, this model data mismatch cannot be attributed to the industry because the signatures don't match. And then you get the result on the right. And indeed, you see that some other sectors are now also updated. For example, 1B, which is coal-fired power plants, and 2A, which is residential combustion. These now also get optimized because the CO-emitted species tell us, okay, this model data mismatch cannot be attributed to the industry. So this looks very promising, but we also have to realize that these emission ratios are very uncertain and highly variable in space and time. So you really have to know these signatures in order for this to work. And this is quite challenging to achieve with real observations. So now I will move to the prior uncertainties. Here you see an emission map of CO2. It has a 1 kilometer resolution. And we try to estimate the uncertainty in this emission map, starting with activity data and emission factors that we use to calculate emissions and our spatial and temporal proxies. And we estimate the uncertainty in all of these underlying data for a total of 112 sector field type combinations. And we put that into a Monte Carlo simulation with 500 ensemble members to estimate the overall uncertainty for such an emission map. And here you see a first result. And here there's no uncertainty included in the spatial and temporal distribution because it's annual country level emissions. But what I want to show here, for example, is that for Sweden or Denmark, you have quite a large spread in CO2 emissions for other stationary combustion. This sector is mostly residential and commercial heating. And these countries use a lot of wood for heating, and wood has a large uncertainty in its emission factor. For example, natural gas CO2 emission factor is much better known. And you see that, for example, in the spread and emissions in the Netherlands, where natural gas is the main fuel used for heating. So next I will show you some results on the spatial and temporal uncertainties, but I want to mention beforehand that we have not yet included spatial and temporal error correlations. This is something that we want to focus on in the next months, but keep that in mind when you look at the results. So as for the spatial distribution, we now zoom in. You see here again the west coast of the Netherlands. Here you have in the middle, you have the city of Rotterdam, and this is the port. And we now use this black box as our study domain. And what we do is create 500 different distribution maps. And then we put that in a Gaussian plume model, a very simple forward model, and we calculate the concentrations at each of these black stars, which are just imaginary observation sites. The first example I want to show you is again for other stationary combustion, and we use population density for the spatial distribution. And you might think, why 50% uncertainty in this population density? Well, the population density itself is not that uncertain, but we use a weighing factor because we know that people that live closer together, like in apartment buildings, use less, have a lower energy consumption to heat their houses than people that live in a detached house. So, but we do not really know what this weighing factor should be. So that introduces mostly this uncertainty. So then you see here in the figure, the spread in the CO2 concentration at each of these receptor sites for the 500 model runs. And what we find is that, well, relatively close to the city center, you will have signals that are definitely large enough to detect with a good in situ instrument, but the spread is also very large. And this is exactly why it's so difficult to do inverse modeling. Even if you have a strong signal, the uncertainty is so large that it's very difficult to interpret this signal. An even more interesting case is public power. The very large power plants report their emissions to a database, and it also includes their exact location. So there's no uncertainty in the spatial distribution of these power plants, but there is residual emissions. So they're coming from these very small power plants that that are not part of this database. And normally we just distribute all these emissions over pixels that have an industrial land cover. And in this domain, that means 280 pixels. And if you do that in a forward simulation, you get these red dots at the bottom. So there's almost no signal coming from it. You do not really observe emissions from these power plants. But in reality, we note that these are actually small point sources, and we estimated that there should be around 20 of them in this domain. So we randomly select 20 pixels from these 280 industrial area pixels. And we do that again 500 times, and then this is the spread that you get. And well, what you see is that sometimes actually you can detect a very large signal if this power plant is close to your observation site. Obviously, when you're doing national scale inversions with ICOS sites, for example, this is not really that important, but the tendency is to go to smaller scales to look at urban sites, and then these kind of issues need to be resolved before you can actually use those observations. So then finally, I want to say something about the uncertainties in temporal profiles. The domain has shifted a little bit. It's still Rotterdam, but now these 3 stars are actual observation sites. So this inversion is done with real observations. And we compared 2 inversions in which the only thing that is different is the temporal profiles. You see here an example of residential heating, and the orange line is the normal temporal profiles. It's based on climatological average temperature data. And that's used in this base experiment. And then we also made a new temporal profile, which is based on actual temperature data for this specific domain and period. And then you get the blue line and you see there's a lot more variability, and that it also better explains the true activity data represented by the green line. And we did a similar thing for public power and road transport. And then we optimized CO2 emissions for the whole domain for 1 month, January 2015. And what is interesting is that we actually start with the same prior emissions. So there might be a shift in which sector is dominant, but overall the emissions for the whole month and domain are more or less the same, and also the prior uncertainty is similar. And what we find is that when we use the updated temporal profiles, the optimized emissions are closer to the prior. And there's actually a significant difference between the two optimized emissions. And we expected that we would simply introduce a random error with these temporal profiles, but it seems like it does have a major impact. And the main reason for that is that it also affects the spatial distribution. So here I made a schematic to explain this. And you see two sectors, road transport and residential heating. And in both cases, the emissions are exactly the same, but here road traffic is the dominant source sector, and here the residential heating is the dominant sector. And what you find is that because these the emissions coming from residential combustion are closer to the receptor side, there's less dilution. So the concentration that you observe at the receptor side is higher, even though the emissions within the domain are the same. So basically, changing the temporal profiles also changes the source-receptor relationship. Then some short take-home messages. I noticed that I was an inverse modeler once myself, and I noticed that when you get emission data, you just want to use it. You put it in your model and you think, okay, this is it. But being on the other side now, I notice it's not just plug and play. It's very important for modelers to think carefully about prior before they use it in an inversion. One example is that waste burning is sometimes included in an inventory and sometimes it's not. But you cannot scale something that's not there. So you really need to make sure that the inventory is complete. It's also important, especially when moving to smaller scales, that the inventory really represents most of the intrinsic variability in the emissions, as in the example I've shown for power plants, the small power plants. And it's very important to define the prior errors correctly. So what I think is needed to improve on CO2 inverse modeling efforts is to spend more time on spatial and temporal variability in the emissions. Again, it's mostly on urban scales, but also to better define the prior uncertainties and error correlations, and something that we intend to work on ourselves as well. And I think it's very useful to include co-emitted species, but it also means that we need to know much better the emission ratios of these co-emitted species with CO2 if we understand them better. And I think a part of the problem can be solved using emission models instead of emission inventories. Then we might actually be able to much better understand what happens within different source sectors than we do now. That's it. Questions?
Thanks very much, Ingrid. That's really fascinating stuff. So Anita has had to go and pick up her children, well, our children from school. So I'm chairing from now on. So does anyone have any questions? I can't see the raised hands thing, I don't think, on my iPad, Aoife. So maybe if you can let me know if there's people with that. I mean, I had a
Alistair's question that he had to run off and Anita
Yeah.
over in the chat window.
Yeah, well, I had a question actually, Ingrid, before we go over to Alistair's question, which, I mean, I wonder if you can give your thoughts on Mark's final question about, you know, is an inversion worth it for anthropogenic CO2? Because I'm kind of looking at your results and thinking, in some respects, if I'm understanding this correctly, you know, you've got these potentially big uncertainties, potentially particularly if we get down to smaller scales on our bottom-up estimates, and so therefore it would seem to say, well, top-down methods are clearly going to, or hopefully going to add value if the uncertainties are as large as that. But then on the other side, I think you're saying that there's so many more facets to these bottom-up estimates that we maybe don't traditionally account for when we do our model simulations, that it could, you know, it could lead to spurious answers. So I'm just wondering where you sit on that. Is it a net benefit, or should we just focus all our effort on the priors?
I think it should be a combination of both. Yeah, I know for CO2, the emission reporting, especially in Europe, is, you know, the uncertainties on an annual scale are like 2 or 3%. It's not really that difficult. But we know that we introduce quite a bit of uncertainty when we distribute them in space and time. And we always thought that part of this error that we introduce is random, but now it seems that sometimes you do introduce quite some uncertainties that are not just that easily resolved in an inverse modeling exercise. So I think we need to better understand the uncertainties in the prior. But I do see the added value of inverse modeling as well, especially when we try to assess the effectiveness of policy measures. But for me, it's more interesting to focus on individual source sectors than on total CO2. And then in combination with other greenhouse gases, for example, which are much more uncertain. So I would definitely also invest in inverse modeling.
Sure, great, thanks. Okay, Hugo, I can see your hand up.
Yeah, oh, and I see I'm also not muted. So, yes, I have a quick remark to Mark's presentation, and I think a question a little bit to both of them. Although I'm of course very familiar with what Ingrid is doing. But Mark showed in the beginning these maps of the UK, right, from the national inventory and the CO and the CO2 and the similarity of those, and then concluded from those that, well, they look very similar. So there must be some information there, which I don't disagree with. But I think one of the tricky things with these maps is that you don't see point sources. They're very high resolution maps. So you have like 1 by 1 kilometer grid boxes, and a point source will be in one of these pixels. So you really don't see that pattern. And especially for CO2, these are still really very dominant. So, and I think this relates then also a little bit to what Ingrid is doing. So where you look at these spatial patterns, those are really, I think, very important for the let's say the area type of sources. So the road transport, residential combustion, maybe things like agricultural related stuff, or also non-combustion CO2 maybe. So maybe a question to both, sorry for being a bit wordy, is what do you think is the added value of going deeper into this point source versus non-point source, and including the co-emitted species?
Do you want to comment on that, Mark?
I can try. Yeah, I mean, it's a good point. And I guess Ingrid kind of made the point a little in her talk, is that I guess point sources will have a big effect when they're close to your measurement site. But the fact that you're not necessarily able to resolve a point source, which is obviously just in a 25-kilometer grid box, by the time you get to 50, 100 kilometers away, that signal will have all mixed enough that that won't be as important. I know Alistair's left the call, but actually I was talking to him a few weeks ago, and he was saying that he's run this through his model. So releasing as a point source at very high resolution compared to just calculating on a sort of 25-kilometer grid. And once you're at a certain, I don't know what distance, but yeah, once you reach a certain distance, those signals essentially become the same. I think it's certainly going to be an issue if we're looking to resolve things at high resolution, at high resolution, and if those sources are close to our sites. I guess, as Ingrid said, she might be able to talk a bit more about that.
Yeah, no, I agree. It's especially relevant for this high resolution modeling, and also for using co-emitted species, because whereas these point sources are clearly dominant for CO2, they almost emit no CO or NOx, or at least not that much. So also for using CO, for example, as a tracer of fossil fuel CO2, I think it's very important to consider that these point sources are there and are really dominant for CO2. Especially going to smaller scales. I agree that if you move farther away, then it doesn't really make a difference anymore, because everything is well mixed, and then it just disappears in the atmosphere. But yeah.
Okay, thanks, guys. So we had a question from Alistair. He says, my question was a comment. For the residential heating, the map looks very similar to the gas distribution grid, i.e. the split between where oil and coal is used compared to gas. Can this information be used to have two ratios rather than just one? The spatial information where gas is used is known.
I think this is a question for me, right?
Yeah.
Yeah. I presume so. So I mean, this is just the mapping that I took off, the way the NEI, Ricardo map this data. So I mean, they would have that information, but I mean, they're providing it as one domestic combustion sector. I suppose essentially that's made up of different what they're burning in different places, I suppose. But yeah, it's just a case of getting hold of that information. I'm sure it's there.
Okay. Any other questions? All right. Well, that's great. Well, thanks again, guys, for two really interesting talks. And yeah, thanks for everyone for their questions. And I guess we'll let you all get back to the football. All right. Thanks a lot, everyone. And thanks again, Ingrid. Cheers.
Yeah, thank you.
Bye.
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 So,
Bye.